All right, so got the quiz today. So we'll start out with any questions from chapter 8.
Number 110.
All right. Grab a prop. So it's a question of when you pull it, which way will it go? And I think the first one's relatively simple. How well can you see that? All right. I think that's going to be viewed by everyone. So part A, when I pull it, I think it's very clear it's going to roll like that. That's not the shock. It's the second one, or the third one. So the wording is the spool is pulled 3 ways as shown. There is sufficient friction for rotation. In what direction will the spool roll in each case? So as I pull on this to the right, which way will it roll? Your gut feeling? Which way will it spin, like that or spin like that? I'm going to pull. It's going to spin, go to backspin. Another backspin.
I'm undecided, I don't know.
Right.
So front spin. It's going to spin like that. It's going to backspin.
I thought it was going to go that way, but then I thought that it actually was going to go that way, and that's why I was confused, because I thought it should go that way.
All right. So as I pull on it, it's a front spin. It's not a back spin. Now the question is why? We are applying torque here. It is chapter 8, so we are applying torque. And wow, this mask is really muffling me. See if we can change it slightly. And we'll see how that goes. Yeah. So we're applying a torque. The question is, where is the pivot point? And this is the part that messes people up. Now the pivot point is the part that does not move at that moment, such as the hinge. Hinge is a natural pivot point. Hopefully I'll get this right. So which part does not move when I pull? At that moment. Eventually the whole thing moves, but... Excuse me?
The center?
What's keeping it from moving? This feels right. It's in fact, the pivot point is here. It's the friction at this point which is keeping this from actually moving left or right. What happens is if we put a spot on this and we rolled it, this spot right here will come down, touch, and then lift back up again. It's not sliding at all. So at that brief moment when I pull, that's the pivot point. Then the pivot point keeps changing because then I have a new point that sits down and that becomes a new pivot point, then another one becomes that pivot point. But in essence, I've got sort of a lever here that I'm pulling in that direction so it spins this way. The whole thing will spin this way. This will spin faster than this will, and so that's why the thing moves off to the right. Now, if I pulled fast enough, overcame the static friction at that point, it would do a backspin. Apparently not. Did it get caught? Oh, yeah, the rope sort of caught on itself. If I can do this backspin, so stop. Nope, it still doesn't want to do it. I've done it before where I've got this spectacular example, but especially on that second one, however, the rope was sort of caught up in itself and sort of undid it. Yeah. Apparently I can't do it. So if I yank fast, it's still going to move off to the right. Just won't roll.
Do you think it might be because it's on the table?
That's possible. Let's see what happens on the carpet. No, pretty much still the same thing. But usually we think of wheels as rotating about the center here, and it depends on your reference frame. But in fact, wheels do rotate about the bottom. Now the middle one, that one's really hard to reproduce because the pull is right there at the pivot point. So technically it doesn't spin, but it's hard to duplicate because as I pull it up, there's a very brief moment where it doesn't spin, but as soon as it's in the air, it loses that pivot point and then it will start to rotate. And so that's just hard to duplicate. Let's see if I can pretend. This is the one where I had the rope caught up on itself and it didn't spin at all. It was just a spectacular example, even though it was faked. Yeah, I need to do it. If I go over too far that way, it will spin that way. If I go too far that way, it'll spin the other way. There's that. Another spectacularly bad physics example. So the first and third case should rotate it should rotate from our point of view clockwise, and the middle one in that brief instant will not rotate at all if the pull is directly in line with the point where it's touching the table. And then right after it lifts up, it'll backspin, because the pivot point shifts from that point on the table to the middle. Did that help? Okay.
Yeah.
Any other questions from chapter 8? Any questions from 8 or 9?
In 34, how do we know when to use the brackets? Because whenever I figured it out, like, I didn't know it was supposed to have brackets, but then I looked at the solutions. and it
Wait,
had
sorry,
brackets.
you're on chapter 9, problem 34? And calculate force of gravity on the same 1 kilogram mass if it were basically the Earth's radius above the Earth. Yep. All right, so, sorry, your comment about brackets, I didn't quite catch that.
Okay, so whenever I didn't like know we were supposed to have brackets around it, and then whenever I looked at the solution, it had brackets around it. So I wasn't sure like when to know if we're supposed to use the brackets.
Yeah, does anyone have the solutions printed out?
I do.
Is that problem 34?
Mhm. Yeah.
Problem 34. Oh. Okay. You're talking about the brackets in the denominator? It depends on how you want to enter it into the calculator. Because we have G mass 1 mass 2 over R. And this square, this is the magnitude of the force due to gravity. And that's a subscript. We're squaring the distance, center to center distance. And so this could be written, the whole thing could be written as 6.4 times 10 to the 6th plus 6.4 times 10 to the 6th squared, just like that. Or 2 times 6.4 times 10 to the 6th but we're squaring the whole thing. And so I would have written it like that, but some traditions are that parentheses and then brackets outside that.
That's the way I had it too, but then I just went back and put brackets whenever I see
Right. If the parentheses were there, the calculator would handle it just fine.
I did the 2 parentheses and it came out right.
Okay.
Wait, in that case though, do you square the 2?
Yes, the 2 is also being squared, and that's one of the reasons why you need that extra set. Because ultimately, in that particular problem, you've got Earth's radius here, and then you have something that is that far away from the surface as well. And so the center to center distance is twice that. Taylor, did that answer your question? Okay. That was not an enthusiastic nod, but I'll take it for now.
I do have a question about 43.
43.
I had a hard time coming up with 9.24. I kept getting like 10 and other numbers, but I could not get it entered in. And I tried it like 8 different ways and still couldn't get it right.
All right, so it's a matter of, let's see, 200 kilometers above the Earth's surface. So it's a question if you weren't getting the percentage right, or?
No, I couldn't get 9.24, so I couldn't even get to the percentage.
How close did you get?
I got to like 10 point something.
Oh, okay.
Yeah.
So it's not, you can't chalk it off to a rounding. So again, we have radius of Earth, and now we're talking 200 kilometers above that. And again, it goes back to, it's not surface to surface distance, but center to center distance. You need to know that distance right there. And this is acceleration due to gravity. Yeah. So I know that the force due to gravity, I have 2 formulas. I have mg, but I'm not near the surface of the planet. Knowing what g is, we have to calculate. And that's going to be equal to, this is mass of object. Big G, mass of object, mass of planet, divided by the center to center distance squared. So the mass of the object doesn't matter, it cancels out. And so we have a formula for the acceleration due to gravity, which is, I suspect he actually has the formula in the book somewhere, but this is what we're using. So 6.67 times 10 to the negative 11th times mass of Earth, 5.98 times 10 to the 24th. Although some will say 5.97, I think Hewitt goes with 5.98.
Oh, that's, hold on. Okay, I don't have 5.98.
What did you use?
In the solution that I printed out, it's 6.67 times 10 to the negative 11 times 6.0 times 10 to the 24th.
Okay, so he just rounded off one step further.
Okay.
And then the denominator, this is where people usually mess up. Again, it's the total distance there, so it's the radius of the Earth. Now at this point, he goes 6.38 times 10 to the 6 meters plus 200 kilometers, 200,000 meters. Make sure that they're in the same units, squared. And so this becomes 6.67 times 10 to the negative 11th, 5.98 times 10 to the 24th, divided by, well, if you add those together, this becomes 6.58 times 10 to the 6th squared. Now at this point, I'm not quite sure where things went wrong on your calculator. If you got that, you got this far?
No, so I'm just following what was the solution on
Right.
on here. And it, like on the bottom, it has in brackets, so it's brackets, the whole thing squared.
Right.
6,380 minus 200 in parentheses.
Minus
times-
200?
Maybe that's why I couldn't get it, I don't know. Times 10 to the third, and that's all squared.
Huh. That should be a plus.
Maybe that's why.
So now the question is that typo or just the printing? Only printed part of the plus sign. And just also, were you okay with the way that they did the addition problem?
I'm sorry, say that again. Yeah, oh no, I got that.
Okay, so you're good with the 6,380 plus 200?
Right.
Okay.
And then
Right.
you just multiply that by 10 to the 6th, or 10 to
Yeah,
the.
well, it's 200 kilometers, just take that piece of it, which is 200 times 10 to the third.
Okay,
The radius of the Earth is 6,380,000 meters, or 6,380 kilometers. So I put it in terms of meters and added. They put it in terms of kilometers and added, and then replaced the kilo with 10 to the third.
okay, that, I couldn't figure out where the 10 to the third came from, but now I know.
Yep. So I find it odd the way they did that, but it's legitimate. It's just
Okay.
not the way I would have done it. All right, so you good on this one for now?
Mm-hmm.
All right, any other questions from chapters 8 or 9?
I'm not really sure what chapter this is from, it was in one of the three, but like, what is really the difference between rotational and like tangential speed?
All right, so if I take, oh, no, that'll one over here. So just picture the arrow right there. Tangential speed is basically this, that's the linear speed. That's what we've been doing, that's what we were doing back in chapter 3. So linear speed is basically how much distance was traveled in how much time, divided by how much time. The angular speed deals with how much of an angle it goes through in how much time. So if I think about, I've got various pieces of tape on here on this wheel, they all have the same angular speed because in the same amount of time they go through the exact same amount of angle, but their linear speeds are different because the arrow has to travel a much greater distance than this piece of tape does. So it'll have a greater linear speed. Now, generally it's called tangential when you're talking about something in a curve, but linear speed and tangential speed are interchangeable a great deal of the time.
Okay.
Is that sufficient?
Yes, what's the formula for rotational?
It depends. So there's a relationship between linear and angular speed, or rotational speed. So linear speed, V, it's the linear, or tangential, often, in the rotational stuff, also called translational. It's just new names for the stuff that we've been doing. Omega is the angular speed or rotational speed. Either one. So the relationship directly between them would be V is equal to omega R. So the linear speed is just equal to the angular speed times how far it is from the axis. So back to the wheel here. A point on the outside here is going to travel, have a twice the linear speed or tangential speed than something halfway. Because it has to travel twice as far here than something here. If we go back to speed is equal to distance over time, angular speed, and that's an omega, angular speed is equal to, change in the angle over change in time. So whatever the angle is divided by time. And usually, typically, this will be in radians. Although it's legitimate to do, say, degrees per second as a unit, not typical to do degrees per second.
Okay.
Does that,
Yes, okay,
Okay.
thank you.
I think it's chapter 8. Right. Any other questions from 8 or 9 at the moment? Right. How about 8, 9, or 10?